the exam on Wednesday?
Wednesday.
That's
Yes.
exciting. Is she like?
So Monday will be just a review day. So we can go over some problems, ask questions about homework. The homework, you just hand it in, it should be graded by then with solutions. So there's no homework next week.
Okay, her dispositions.
Review and follow up.
My dad was like off to college, community with the students, so we're coming to touch again. So she took it. Yeah. Yeah, so like I sent her home and yesterday just like gosh, continue to get work and she woke up with me. Thank you. And so then she went to the rescue like town and transported her to her hospital.
Okay.
So like now everything is good now. But
There's a faculty meeting next door, so if they get too loud, you can go over and tell them to calm down a little bit. So, a couple people are gone, so it's a little bit smaller, but we'll talk about things on the exam. I'll post some study problems soon. Certainly this weekend. Probably I'll try to do it sooner rather than later. But it'll be some past exam problems that I've done for this course or similar courses, and we'll can discuss those on Monday and other questions about the exam. So Monday, just review. The exam is Wednesday in class. There's not any homework due, and then we'll take up the topics after that on that Friday. So. Yep. I will look at some of the statistical properties again, but this time it's simulation. We can do that to some extent, and then talk about the multinomial distribution. Yes.
well, after the exam, will the homework be due like the following? What for the next?
Probably the next Wednesday.
Okay.
Yeah. Yeah. So the week after that. Yeah.
Okay.
Yeah. So is that similar to what's on the? I think that's similar to what's on the schedule.
Yeah,
But-
because we have our like October break, so I just wasn't sure if it was.
I think the syllabus says that like the homeworks are due on Fridays after the first exam.
Well, so
It might be an accident.
we'll talk about that. Yeah. So that it won't be due that Friday after the exam. So
That'll be
it'll
Friday.
but yeah, probably the next
Okay.
week, something like that. So. Right. We can double check that. We can go over that on Monday too. So on the exam, right, that we've oops, on this exam one, right, we've looked at chapters 3, 4, 5, and some of 6. So I'm thinking of probably 4 questions, probably 1 coming from each part. The questions might have 2 or 3, A, B, C parts to them, around the question. So the goal is not to make it really long, but at the same time, you won't want to go spend a lot of time on one particular part, but hopefully I'll try to write it so that it's doable. I might just shut the door. It's a little noisier than normal. Next door. So in the some things that you can look at, there's the lecture notes. Oops. Let's see, lecture notes that we've gone over. There's the material in the textbook, and there's the homework and homework solutions. So I'll look back over the homework that's assigned and the homework solutions as I write the questions, so that it's kind of tied to some of those things. Chapter 3, material, introduced, hypothesis tested. So with that, stating the null and alternative hypothesis. So it would be some problem context that will be describing. We're interested in studying this, looking at the average income or average scores, comparing groups. It'll be some context. And so stating the null hypotheses will be stating some null or alternative hypotheses. Can use symbols, but can also be stated in context. We then calculate a test statistic. And we're interested in finding a p-value and then assessing statistical significance. Statistical significance. And to assess statistical significance and do that interpretation, we needed to look at a null distribution. Very good, thank you. A null distribution for looking at the, how do we judge that test statistic. One way we did that was with a permutation test when we had two groups. Under the null hypothesis, there is no difference. A measurement could either be in the first group or second group, and it was just purely random which side it ended up being on. So what can you do with that? I can give some data, some numbers, and maybe based on that you can calculate the test statistic, like the average or a standardized value of some sort. In terms of finding the null distribution in the permutation test, we've done a lot of description of how you do that. Right? So you might write it out in words. This is what I would do to evaluate the null distribution. This is the simulation that I would do. We've kind of written things in kind of pseudocode. You know, it's not in the exact R code that we put on the board, but it's like we would put the observations together in a group. We'd randomly pick in one of them, call that the first group, calculate the average of those. The others that were randomly left out get called in group 2, and we calculate the difference, and we do that whole thing a bunch of times, right? And that would give some null distribution. So being able to describe that general procedure, what you would do would be, describing that distribution. Then, if I would simulate that for you, because you're not going to have the computers with you, I would show you a graph or summary statistics about that distribution. Like I would show you some graph, and it might be something like this, right? And if you calculated your test statistic and it was out in the tails or far away, you could make a conclusion. And I might give you cut points of this. Like if I gave you the kind of the tail areas, beyond certain points, you could, maybe it's the 1% tail and the 2% tail and the 2.5%. And then, and if your value was there, you could use that to make a conclusion. Right? So because the test statistic is out beyond the 1% point of the simulation, that's unusual. Therefore, I reject the null hypothesis. So it's focusing really on the logic of setting up the problem, describing how you would do the test, and then interpreting some results where I give you some graphs or things to make that possible. So we did that with two groups. We also did some of that with, so either two groups. We also did this with matched pairs, where you would take differences. So then the description of the algorithm and what you would do would be a little bit different, right? Because you're talking about, do you flip them as the pairs, group 1, 2, is it this way or this way? And so we would either get a negative. So that type of testing. That was understanding that process and working through it. That was a lot of the content of chapter 3. Chapter 4 looked at sampling distributions of statistics. Sampling distributions. And so what do those mean? Every once in a while we could do exact distributions, but that uses more probability theory to actually get that. I'd probably tell you this is the sampling distribution associated with some statistic. What does that mean? What does it mean when I say this is the sampling distribution of the statistic? There could be simulation. And this was kind of the bootstrap type approach to doing, simulating the distribution. Like you'd have data and you calculate the average. What does the distribution of the average look like? Well, if you resample the data, you can calculate more averages. You can do that many, many times and get some idea of these. There was also, so primarily I'd give you you describe the simulation procedure. How would you simulate a sampling distribution? And if I give you results of simulating, what do you summarize? Means, standard deviations, intervals, things like that. Another way we did sampling distribution was approximate, and this was the central limit theorem. We used results like x bar is approximately distributed as a normal centered at its mean, and its standard deviation is sigma over the square root of n. Or we did p hat, where we did some of these calculations. The sample proportion was approximately by central limit theorem. Normal centered at p, and its variance was p times 1 minus p over n, and we took the square root of that whole thing. So we did some 1 minus p in there. So we did some calculations based on those. So in general, an expression is what do we mean by a sampling distribution for a situation, and then some way of evaluating something like that. Right? So kind of a mix of describing the general case, describing how you would simulate it, and then using it a particular form should be done. Chapter 5 then uses this idea of sampling distributions with Bootstrap to get us our confidence intervals. Bootstrap and confidence intervals for a parameter. So how do you describe the Bootstrap procedure? Right, when you had one sample, we could use that to calculate a Bootstrap standard error. We could look at the Bootstrap percentiles. I guess that was a popular way of getting an interval. Right? You have a statistic, you bootstrap 1,000 times, and then look at the central place where those are. We did it either with one sample. We also did it a two-sample case that was a little bit more involved. Two-sample case, right? Because then you had to bootstrap one group and get an average, and bootstrap the other group, and then take differences. So that was a little bit more involved. Two-sample case. We also had, matched pairs, which was really kind of like the one sample bootstrap. We've already taken differences. So why don't we, if we're bootstrapping, why don't we take X in a matched pairs case, why don't we bootstrap the first measurement and then bootstrap the second measurements and take the differences? Why is it important to bootstrap? Either take the differences and bootstrap them, or bootstrap rows, and things like that. Right? So why do we set up the algorithm to simulate it that way? I don't plan to ask anything about bias. There was some calculation of bootstrap bias that we could do a little bit more, but we didn't focus on that. We did it on one homework problem, but we'll use it to make an interval is the more common thing. I haven't mentioned that those various graphs might be associated with things. So we might show some histograms to illustrate data or illustrate the results of a bootstrap. perhaps a box plot to some degree. What else did we do? There was the cumulative distribution functions, right? Which were a little bit maybe not as common, not as familiar from other introductory statistics courses, but they are used, right? So if you do have that, it would be clearly labeled as the cumulative distribution function. And what would that mean? It might get used to some degree. Right? There was also a normal probability plot, which is the Q norm command in R. This was the one where we plotted the theoretical normals on this side and the actual data sorted on this side, so that if it got a straight line, that means that they were kind of proportional to each other. Right? But if it's skewed or there's an outlier, then the data won't be proportional to the normal, and it will be off from that line. There wasn't too much formally to do with that in terms of judging how normal is it or how, it wasn't formally testing that, but it gives some indication. Right? So that might be useful if we want to look at the bootstrap distribution to say, is the bootstrap distribution normal? There were a couple things in bootstrap that were kind of interesting, right? There was the sample size n from our original sample. How many data points do we actually have based on measuring something real? And then there was the bootstrap replications. Why do we bootstrap 1,000 times or 10,000 times? And why would we not bootstrap 20 times? Right? Why would they be too small? Right. Well, 20 times, sample size 20 doesn't tell you much about the distribution. It wouldn't be a very good illustration of the sampling distribution if we just did it. So these we had kind of different roles. This one affects the accuracy of the data, of the confidence interval and everything really. This has to be large enough to get a good picture of it, but doing more here isn't going to compensate for a small sample size. You're not going to fix your data by pretending you've done it many times, right? So some of that's description, some of this would be numbers, right, to put things together. Right. So that was the chapter 5. But and then chapter 6 that we're working on is mostly maximum likelihood. Chapter 6, 6.1, finding a maximum likelihood estimator. We'll do it just with one parameter. So this is going through what you did for the last homework. You have a certain distribution in independent observations, multiply them together, group together terms, logs, derivatives. And so it'll be something that you can actually solve it. Right? You can actually go out and find that estimator. Okay? I won't put method of moments on there, but in terms of properties, there's kind of the general idea of what some of these properties are. And we'll examine it in a simulation on the final, on this exam. So you could look at the properties by doing mathematical, the expectations or variances and some calculations like that. That would rely more on the distribution probability theory. But like today, we'll look at a simulation and see, kind of simulate bias, simulate variance, or look at the sampling distributions. And if one's more narrow and more centered around the actual parameter, that's better. So we'll have some idea of the properties. But it's also expressing what properties do we want it to have, why are some of those important, and it's really properties of that sampling distribution. So some expression of that. So that's what we've done. It kind of lays the foundations for a lot of things that are done in statistics, but that would be the scope. Right? So it's a mix of doing some things with numbers. You won't have to give me any R code or do any programming on that, but you likely would have to describe one or two procedures or simulations, right? So in words. So you can practice that. Right? We've done it, I think, a number of times for the different things. The book has its version of describing those things, and that's something you can get ready to explain. So, any questions about the plans for the exam? So this next week, the weekend and the next week is a chance to review some of these things. I'll get some problems posted where you can do some practice, and we can go over some of those or questions that you might have. Right? I'll try to get we'll get the homework back on Monday and go over any main questions that seem to come out of grading that. Good. So, okay. So, for today, I wanted to look a little bit more at the properties of estimators and look at one more example. Right, the example today, x, our random variable, is going to be something called log normal with parameters mu and sigma squared. So if y equals the log of x, natural log of x, then it's distributed as a normal random variable. So if you generated a normal random variable, then x equals e to the y. And so it's a normal variable, but it's exponential. That's how it comes up. Right? It turns out that the expectation of x is e to the mu plus sigma squared over 2. And the variance of x, that's the expectation of x. And the variance of x is e to the sigma squared minus 1 down here times e to the 2 mu plus sigma squared. So it means that the expectation of x quantity squared is e to the 2 mu plus 2 sigma squared. Right. So these are our first two moments of this distribution, and it involves the two parameters. Where did this come from? Log normal is discussed many different places on the internet for use in scientific applications, finance applications, and some textbooks would have this as describing these things. So you could look these things up. Right? But if we have n observations from this, and we want to estimate mu and sigma squared, both of them, what do we do for method of moments? We're going to set these two things equal to our first two sample moments, m1, or 1 over the sum of the xi squares, and that's the second moment. We're going to set these two things equal to the sample moments, and then solve for our parameters. And that will be our method of moments estimators. So to do that, I'll write it on the next page. So the first equation becomes m equals e to the mu plus sigma squared over 2. So let's take the log. The log of x bar, or log of m1, equals mu plus sigma squared over 2. Right? The second equation, our second sample moment, was e to the 2 mu plus 2 sigma squared. So if we take log of that, right, it's 2 mu plus 2 sigma squared. And we multiply this thing by 2 times the log of the first one. Right, there's a 2 mu plus sigma squared. We have this equation and this equation. So we can get rid of one of the parameters by taking a difference. Right? If we take this one, right, minus this one, right, the 2 mu's will go away, and we'll just be left with 1 sigma squared. So sigma squared is going to be estimated as log of the second moment minus 2 times the log of the first moment. Yeah. And if we multiply this thing by 2 again, right, so 4 times the log of this is 4 mu plus 2 sigma squared. And now we can subtract 4 times that one from this one, or subtract this from that one, right? And that'll get rid of the 2 sigma squared. So we can get 2 mu, doing the difference is 4 log m1 minus the log of m2. Or mu is 1/2 times 4 log m1 minus log of m2. And so here we got our 2 method of moments estimators for those parameters. Right? That's the nature of doing that. Right? Using that method to come up with estimators. I don't plan to put method of moments on the exam. We'll focus on MLE, which we're going to do next, but this is how that would go with that. But any questions about? So if I had given you, the mean and the second theoretical moment, and you equated those, it would be going through that algebra to work it out. The density, right? We might also do maximum likelihood. The density for x, so x is actually greater than 0 in this, for this log normal distribution. And it's very skewed, like a very skewed income distribution. There's an x sigma square root of 2 pi here. Then e to the negative natural log of x shows up here, minus mu squared over 2 sigma squared. This is an x. And so x shows up here, and it shows up here as log, right? And so if we have independent observations, the joint density of x1 to x2, up to xn, is the product of this thing over I. Right? So maybe I'll put in little eyes on here in case it's helpful to see those eyes on there. Right? And so the product over all those, right? Well, there's 1 over a product of the xi's down here. There's 1 over sigma raised to the n power, because each density has 1 over sigma in there. There's 1 over the square root of 2 pi, because each one has it there. And then each one has e to a power, and we're going to add the exponents up there. Multiplying them e to a power together, all the exponents add. So there's negative 1 over 2 sigma squared, and then a sum of the natural log of xi minus mu squared. That's our likelihood for the 2 parameters. Kind of looks normal, right? But logs show up in there, and there's this extra term that shows up down there, right? All right, so maximum likelihood, we're going to take derivatives to maximize this thing, and it's easy to work on the log scale. So if we take the logs, so this is our likelihood for both of these things. If we take the log of these 2 things, and on the exam, it'll just be a one-dimensional thing, so it'll just be 1 parameter to worry about. Right? I could make a problem like this, like maybe I'd put the sigma equals 5 or 3 or something, and then you'd have to do it from u, right? Or put in a number from u, maybe call that 0. Right? And then, so I'm not actually going to write down these things that don't, once you take the logs, these 2 things don't involve either parameter. I'm going to skip that. I'm going to write negative n log of sigma there, and then minus 1 over 2 sigma squared, the sum of ln of xi minus mu. that's the log, ignoring those two pieces that don't involve the parameters. So once I take a derivative, it's going to go away anyway. And so, for instance, then I'll take a derivative with respect to mu, right? And it's only going to involve this part actually. So these are partials. There's no way around it. These are partial derivatives. We're dealing with two. It's like, right? And the mu one, once you do it, right? There is negative 2. There's a sum of ln of xi minus mu over, there's a 2 sigma squared here. We set that thing equal to 0. That's equivalent to the sum minus mu has to be 0 for that to work out. And so if you split this is the natural log of xi equals n times mu. So mu hat for the maximum likelihood estimates is the sum of the natural logs over n. So it looks different than the method of moments by quite a bit. Right? The method of moments, you took the average of the x's and then the log of that. This is taking the log of the x's and then the average. So they look kind of fundamentally different. If you go through the partial derivatives for the sigma, the answer you get for the maximum likelihood estimate is the sum of the natural logs of xi's minus the estimated mean of mu over n. So again, that one looks quite a bit different than the other one as well. So we have two different approaches, two different estimates. And which one works well? Which one works best? Well, instead of doing the distribution theory, we're going to simulate data from a log normal distribution, calculate the two sets of estimators, right? And then see how they compare to parameters. Right? We're going to use simulation to get some idea of what's going on and their performance. So the handout, one side of it has something there. So we're going to simulate. So I'm going to set some random number c to today's date. Imagine I have 40 observations, and I'm going to have a mean of 1 and a sigma of 5. Just to do one case, right? When you simulate to study things like that, you got to choose some, and it's good to choose a whole variety of different settings to see how they go. But generating a random normal data would be like this, with a mean of 1 and a sigma of 5. The log normal is that exponentiated. So there's 40 observations. This is what they look like. Pretty skewed, kind of crazy skewed, right? Because you get the exponential e to the, exponential, say, to 3 is 20. But these are centered at 1 with a standard deviation of 5. So if you had the mean plus about 2 standard deviations, it would be plus 5, right? So e to the 11th is 59,000. So if you happen to be one of those normals that's kind of out there, it's like really out there once you exponentiate it, right? On the other side, if it's small, e to the exponential excessive mean of this one is about 2.7. So it's quite small. Anyway, this is really, if you take the log of the x's, we should be back to a normal, right? So if you take the log of the x's and the histogram, it looks pretty normal. I mean, it's not perfect, right? Maybe if we do, what was it in class, 10, a few more, so depending on how it breaks it out, it can make it look different. So that looks a little bit less crazy. The maximum likelihood, right, said to take the log of the x's and take the average. And then the sigma squared, right, would be the sum of the squared deviations of the log on the log scale. But the variance function divides by n minus 1. So I'm going to multiply by n minus 1 divided by n to make it divide by n. Right? The default is, for calculations, usually divide by n minus 1. But we can get around that. So those are those two numbers, and here's the two values. So I got 0.08 for my average, a little bit smaller than 1. And then what, 4.6, which is pretty close. That was set at 5. So it's not quite as bad. Right? These are what I think I've implemented the ways to get the mean and the variance using the method of moments one. Right? So it's a log of the mean, log of the x's, the mean of the x squared, and so on. But the first moment is mean of x. The second moment is mean of x squared, and it can be done just like that, and so on. So I calculate those two things, and I get mu turns out to be 5, and sigma 2 equals 1.7. That's just one example, right? You could probably check that to see if it gets somewhat close. They kind of seem away from that, so maybe that's not so good. So just one sample doesn't really show you which estimator is better. We have to see how it does over the long run, right? So we'll generate 10,000 samples from that log normal and see what it does. So I'm going to do 10,000, and I'm going to set up now vectors to hold copies of those things, right, that have length 10,000. And then I'm going to, what does it say? This loop, I'm going to go through, this loop means go through 10,000 times, generate my x, my normal, my log normal data, calculate my maximum likelihood estimators, and now store it in entry B for that simulation, for that replication. And then the method of moments ones. Right? And I think there's a bracket to close that off over here somewhere. So that's the simulation, right? It doesn't take too long to run. Yes. And then I'll look at the properties. What properties can we look at? Well, bias. Right? What is bias? Right? It's the average of your simulated estimates. How close is it to the truth? Right? This is bias. The mean of your sample estimators minus the mean, and this one. Right? And you can do mean. You can do bias of the estimate of sigma. Right? Sigma is the standard deviation. You're estimating that, and so that one has a bias too, possibly. So how do they work out? Mu1, maximum likelihood. That seems kind of small, 0.006. Right? So the average, let's look at that, the histogram of mu1. That's the sampling distribution of my maximum likelihood estimator. Right? Pretty much centered on 1, right? With some variability. That looks promising. Right? The histogram of mu2, however, is funny. Something's kind of gone bizarre with that. And we can talk about that. But if we calculate bias for that one, its bias looks like about 6 points. Right? The average of the sampling distribution does not look like 1. Right? This method of moment in this case seems to be kind of severely biased. If I've done all the programming and all the calculations right. And I think I have. I checked it because it seems kind of far off, but I think it's right. Sigma 1, maximum likelihood, again, looks pretty good, right? It's supposed to be 5. The maximum likelihood estimator in this case is really centered around 5. It's low bias. That's good performance, right? This other one looks kind of bad. Right? The method of moments one has this funny shape, right? You know, it's again, you know, I might go back and try to figure that, but it looks funny. So in terms of bias, the maximum likelihood looks a lot better. Well, we can do variance of the estimators. Right? The variance of the two means. The maximum likelihood one, mu1, see its range is only that far, kind of plus or minus about 2. So its standard deviation, its variance of this distribution is about 0.6. Square root of 0.6 is about 0.8, about. It's a standard error. But for sigma 2, this, for some reason, the sigma 1 is very tight. This is a smaller range than the other one, but it was clearly biased. It was not in the right place. It was not at 5. It seems to get very similar things. So the second variance estimator seems to be less variable, but that doesn't matter. It's still no good if there's a bias. There's something called coefficient of variation, so it's standard deviation relative to the actual mean. So sometimes that's used as another summary. The coefficient of variation for this, the maximum likelihood is about 78%. That's not great. You usually want it to be much smaller, which would suggest that we maybe should have a much bigger sample size for this problem. But it's much worse for it's even worse for the method of moments one. Putting those together, you can do mean square error. Here's a couple mean square errors. The mean square error for the maximum likelihood estimator is this 0.61. And then, because of that huge bias, right, what's dominating this? This huge bias in there for the second one is just makes it bad. So you can study some of these properties with simulation, and the key is, like for this with sigma 1, if the real parameter value is 5, we want the sampling distribution to be tight around 5. Right? And so bias is centered at the right place, variance, how to spread it out, and mean square error to kind of combine those two things. We can study those properties through. What do you think is going on with this method of moments thing? Why does it seem to be kind of, did I make a mistake? Did we find a mistake? Or does it? This distribution is tough because of the skewness. Right? If you get something that's 2 standard deviations out, right, you get 59,000 as a data value, right? And averaging those directly is crazy, right? It doesn't work so well. So method of moments for this one just is not a good idea because the huge, it could be unbiased, but we just have such huge variability that things are kind of chaos, haywire. I want one way to deal with that is to make the sample size 400, because then you're averaging more things together and it should work out. It could be that my sigma is too big. So let's say I make this 1.5. Right. Then say I'm at the mean plus 2 standard deviations, or even plus 3 standard deviations would be 4.5. That number is 244. So I'm not going to get many data values past 244, 250, whereas when the standard deviation was 5, I was way out there, and that didn't work so well. So if I do run through this, if I make it 1.5, and I run the simulation all over again, right? Now the bias is not quite as big. Right? The mu's, there's less bias there. The variances are more comparable, and the sigmas are more comparable. Coefficient of variations, MLE still a little bit better. Mean square error, MLE is still better than that. So I think in that one simulation, because it was such a skew distribution that things went nuts, and because taking the average of something so skewed, the estimators were just highly unstable. But if it wasn't quite that bad, they're a little bit more comparable, things like that. So we can study some of the properties through simulation. And the key is getting that sampling distribution right around the estimator, and then it's going to work out well. But any questions about it? So one thing to kind of finish up is related to something that was on the homework. A particular distribution is called a multinomial distribution. Where it's kind of like a binomial, but instead of success failure, you have multiple categories. So in the Rock and Roll Hall of Fame, which is in Cleveland, has anybody been there? It's pretty fun to go sometimes. You want to go and see all the costumes and guitars and everything, videos. At one point, I think it's a little bit dated now, there are 303 individuals in there. Some of the people are in there as early influencers. Right? 31 people were there. Some people are in there for lifetime accomplishments. 10 at that time that this was data from. There are some people who are non-performers. Maybe they're agents or producers or something like that. The largest group is performers, 206. And then there's side personnel. There's some people who were never the lead in the songs, but they played with tons and tons of famous people, so they had some profound influence. Right? So these are the counts. Maybe you would call this N1, N2, N3, N4, and N5. 5 groups there. In this example, K is 5. There's 5 groups. And the idea of this distribution is you randomly pick somebody and they get classified into one of those categories. And the classification, the chances that they're classified into one of the categories are these different proportions. So there'd be a P1, it'd be the proportion here, P2, P3, P4, P5. Right? And these proportions add up to 1. So the goal is to estimate those proportions from the data. And the data we have are the number of times that each one of those categories comes up. Now there's a probability model for this, just like there's a probability model for binomial, or like the genetics things you were doing on the homework, right? Really do fit this category. Instead of having 4 separate probabilities in the genetics case, they were all related to one single parameter. So it reduced from 4 categories to 1 key parameter, right? And then you did maximum likelihood for that. But in other cases, it doesn't reduce as much, or there might be multiple parameters. Right? So the probability of seeing N1, N2, N3, N4, and N5 in this case, there is a combinatorial thing out here, kind of like in the binomial, about rearranging the, you have 303 individuals, and it's not necessarily the case that the first ones are performers or the first one are early influencers. They could all be mixed up. So how many ways can you do that? That's this little combinatorial thing that won't change things. Oops. P3 to the N3, P4 to the N4, P5 to the N5. Right? So this ends up being the probability of the sample. Right? Where we have our proportions, and we have our sample points here, like that. Right? And so maximum likelihood is we want to find the values of P that make the data most likely. Same approaches as for the other ones, right? So this is the likelihood for our proportions. What if we try our ordinary routine here of taking the log of this? Well, there's a combinatorial piece out here that doesn't involve the p's. So I'm just going to, there's a constant. I'll just call it a constant. Right? So then the log of this thing, right, becomes N1, the log of P1. Right? And then there's an N2 log of P2, N3 log of P3, N4 log of P4, and then a N5 log of P5. We get those 5 things there. Make this one nicer. So we want to find the values of P that make that as big as possible to maximize it, right? What happens if you take the derivatives with respect to one of those things? Well, if you just kind of go and do it, right? The log of L of P1 you get N1 over P1. And these things don't have P1 in them, so it doesn't happen there, right? And you set that equal to 0, and you're kind of left with a, what's going on, right? How does that work out? P1 can't be infinity, it has to be a proportion between 0 and 1, right? So something's going on with this one. And the key to the thing going on in this case is there's a constraint, right? Because in these multinomials, P1 plus P2 plus P3 plus P4 plus P5 is 1, right? So they're not really 5 independent proportions. They have to add up to constraint. They're also all, the piece of j's are all greater than or equal to 0 unless they're equal to 1. So they have to be in that range too, but there's this constraint here. Right? So how can we deal with that? Well, there's two ways, really, numerically, that this gets dealt with. Right? And so if you take a class in scientific computing, computational issues, for dealing with things like this, you deal with constraints, right? Operations research, economics often deals with these things, right? So one option is to replace one of the p's by some solving for in terms of the other ones, right? So if you do that, right, so one option is some type of substitution. Say take P5 is 1 minus P1 minus P2 minus P3 minus P4. Then, if you take the derivative of this log, and it's a partial, with respect to the first one, you get the N1 over P1 here. But then P1 shows up in the last part, right? So P1 would, just like we had before, we had this part, would still be there. But now there's a 1 minus P1 over here. So you have to take the derivative of that part. So you'll get, there's an N5, and then 1 minus P1 minus P2 minus P3 minus P4. And then because of the negative there's a negative there. And you set that equal to 0. Right? Well, there's another equation for P2. There's another one for P3, and there's another one for P4, right, and all those, you said those is equal to 0. And so you end up with 4 equations, and there's 4 unknowns, right? And so then you have to solve that thing, right? But it's doable. You could take the first one, solve in terms of P4, and then plug P4 into each of those. And then take the next one and solve for P3. It's tedious, but you can do it, right? One other way of, so any questions on this? So is this kind of straightforward? You don't have to deal with that constraint, so you can replace one. And then when you take the derivatives, you get something that you can do that same thing, right? The overall goal is familiar, right? We want to find the p's that maximize. And this, because of the constraint, you have to use that constraint when solving. That's all this is doing. But on the back of the handout is another way to do these type of problems with constraints. And it's called Lagrange multipliers. Now the constraint that the sum of the pi's equals 1 can also be 1 minus the sum of pi equal to 0. And the numerical maximization trick is to put in an extra parameter, right, that then you can solve for. Right? Put in a lambda, and this is all, like I've written on the handout, you take lambda times the sum of the pi's minus 1. That becomes a Lagrange, so-called Lagrange multiplier in this equation. So now, instead of trying to solve for the log likelihood by itself, there's all the p's there, you add this extra piece that has the constraint in there. So now when you go through and take the derivatives with respect to the p's, you get another piece. Right? You do all 5 of them, but because you have this extra lambda in there, it kind of takes the place of one of those things. So instead of going through the math, because you won't get a question like this on the exam, I just think it's an interesting technique. I find it very useful in a lot of optimization problems in higher statistics classes. There's constraints on sample size, there's constraints on proportions, and so on, to be able to recognize, oh, I might want to try this. So, I have the scan. Let me go to here. I scanned this, so there it is. Open up this thing, right? So when you take the derivative of this thing now, you get, I used x's instead of x1 through x of k instead of n. Sorry, switching. You take the derivative, and now there is an extra lambda there. So you get this equals this, you rearrange it a little bit, and it looks like that. But you do that for all of the different equations, all the different groups. And then if you add across it, you get the sum of the x's equals lambda plus the sum of the p's, and that equals 1, this equals n. So you discover that this lambda, this mysterious extra parameter I've stuck in there, has to be equal to negative n. Which means, if you go back up to this equation here, p1 equals negative x1 over lambda, but lambda is negative n, so p1 is x1 over n, just the sample proportion in that group. So that solves it. I often find this to be quicker and easier to do than substituting in through 5 or 6 equations or something like that. Right? So for rock and roll, example, what was that? Right, the estimates, the proportion, the estimate is the MLEs that we get in there, P1 hat is just the number in that category over n, so 31 over 303. So the early influencers had about 10% for the earlier influence category. The performers, this category, PN4, the 206 out of 303, was about 68% a few years back, and so on. Right? And you can do that with all 5. And that's the maximum likelihood for multinomial. It's doing the same type of thing. Right? This also comes up in other very famous problems, right? So in bags of M&Ms, there's browns, yellows,
Green.
there's red, there's green, right? Yes, orange, green, and there's actually blue. And in the 1997, apparently there was a website that said they were at 30%, 20%, 20%, 10, 10, and 10. Right? And so, what is it now? What's 2019, 17? Are we? What's the distribution? Have they changed the mix? Right? And so this is a multinomial problem. If you have a certain number of M&Ms, say about 15, you could count and see how many you would come up and do maximum likelihood estimate. So to do that, you have to have data, right? So I brought some data, and you can, if you want one, you can take one. Sorry that it's missed, so I'll have to come by office hours to get there sometime. Can't get it open. I have a couple old Skittles and you don't like M&Ms. Do you like M&Ms?
Thank you.
So if you want, you can open. Oh, it's not letting you. Right. You can be sure to count your browns, yellows, and oranges, right, and keep track of these things before you consume them. And then we'll put up some data and see what we have. How is it doing? These, you not eat chocolate or Skittles? Do you want one?
Oh.
These are, they're a year old, but they're probably not, you won't have the same color distribution, but you're welcome to it if you want it. How's, you know, it might not go bad stale, so,
Thank you.
yeah. There are, I can't adjust for all allergies, but something, right? We might even be able to just get it in here, right? So the process of recording data, summarize what you get, and maybe we can add it all together. So I have 4 blue, 4 red, 2 yellow, 3 orange, 2 brown. That's my 15. What did you have?
I had 6 red,
6 red.
3 brown,
Uh-huh.
1 green,
1 green.
4 orange,
Uh-huh.
and 2 blue.
2 blue. No yellow, huh? Right. What did you have?
5 brown,
5 brown.
1 red,
Mm-hmm.
1 yellow, 2 blue, and 5 orange.
5 orange and no green. Huh?
Mhm.
Right. What did you have?
1 green,
1 green.
1
Uh-huh.
yellow,
Uh-huh.
4 blue,
4 blue.
3 brown,
Mm-hmm.
and 3 orange.
3 orange.
4
No.
red.
4 red. Okay. Yes.
3 brown,
3 brown.
1 yellow,
Uh-huh.
1 red,
Uh-huh.
5 orange, 2 green,
Yeah.
3 blue.
3 blue. And Vic, what did you?
I had 1 brown, 2 yellows,
Uh-huh.
1 red, 3 orange, 5 green, 3 blue.
And 3 blue. Okay. Yes.
I had 2 brown,
Uh-huh.
2 yellow,
Mhm.
0 red, 6 orange, 3 green, and 2
Mhm.
blue.
2 blue. And
I
then you?
have 2 browns,
Uh-huh.
4 yellows, 0 red, 6 orange, 3 green, 1 blue.
1 blue. Connor.
2 brown,
Uh-huh.
2 yellow,
Uh-huh.
2 red, 4 orange, 2 green, 4 blue.
4 blue. Oh, so you got an extra one, I think, so. Right. So did any of the numbers kind of look inconsistent with the previous
Orange.
state? They're orange,
Orange.
right? You'd expect
Yes.
1.5 over here. They're all high, right? What else is? This one looks a little bit, you'd expect 3, right? Eventually we'll get to testing, right? But assuming these are all independent samples, if we added them all up and added up the total, that'd be the estimate over here. So maybe we'll keep these data and or add to them as we return to chi-square testing and things like that. So that's it. Monday, I'll post some stuff over the weekend. Monday we'll have some review. Maybe we'll come back sometime. Or if you stop by office hours, maybe I'll give you some. Have a good weekend.
You too.
What provide does it today? Sorry. Go ahead. No, it's right.